Hey there, here we go into the applications of the derivative of e to the x. And just like the natural log of x, there's nothing new here. It's, do you know your derivative of e to the x? And if so, let's apply it to old school derivative concepts. Don't you love that they're old school? We've done them before. So, in other words, if you have a problem like find the equation of the tangent line to y equals e to the minus 4x at 0, 1, you're essentially being asked to fulfill this goal, right? We want y minus y1 equals m times x minus x1. Right, it's something simple you've done many times before. We need the slope. We've got the point, right? Here is x1, here's y1. We just need the slope. How do we find that? Well, we need the derivative of e to the minus 4x. And that's going to be e to the stuff, d stuff. So the derivative of minus 4x is minus 4. And we're going to evaluate that derivative at 0. So a little funky notation here. So that's the derivative evaluated at the point 0, 1. So we'll plug in x equals 0. You're going to get 0 in the not the denominator, in the exponent times negative 4. And so that's e to the 0, right? Essentially, you get e to the 0 times negative 4, which is 1 times negative 4. So the derivative is negative 4 at 0, 1. That's it. Nothing super complex. And we plug in our information. Y minus 1 equals the slope, negative 4 times x minus 0. And leave it in point slope form. That's it. So old school concept with your new school derivative. Not bad. All right, let's keep cruising. So if you're asked to find f prime of x given an integral where you've got capital F of x equals the integral from 0 to e to the 5x ln of t plus 4 dt, we follow the second fundamental theorem of calculus, right? That's what's being asked here. You're taking the derivative of a definite integral, right, with a bound that has a variable in it. So that's going to be the derivative of f of x, which will be plug in e to the 5x into the function in the integrand. So e to the 5x goes in for t, not bad. And then we're going to multiply by the derivative of this bound. So that would be times e to the 5x, e to the stuff, d stuff. So nothing new there. Very quick problem. So we'll get 5e to the 5x. I'm going to swing that out to the front. ln of e to the 5x plus 4. That's all. Not so bad. Not so bad at all, right? So old school concept, new school derivative. You got this. All right. One last type to go over here before we get into the exercise videos. It says find all local extrema and points of inflection of 2x e to the minus x. Okay, if you're looking for local extrema, relative maxes and mins, we're looking to see what the derivative is doing, its sign. So we need to find critical numbers. Then we're going to do a sign chart, check out the signs. Points of inflection, we'll need the second derivative and check out where the signs change from positive to negative on the second derivative or vice versa. All old school stuff. So let's start out with the derivative. We got this. F prime of x equals, well, we're going to do first d second, first function. And now the only new part is this part, the d second, because it's e. So that'd be e to the stuff, d stuff, the derivative of minus x being minus 1, plus the second, so that's e to the minus x, d first, which is times 2. Sweet. So now from here, what we've got is this really funky looking function, but I always recommend, especially with e, because e doesn't go away when you take the derivative, to factor it out in the greatest common factor. You have a 2e to the minus x in each term. So we're going to take out 2e to the minus x. You'll be left with x times negative 1, or minus x. This is just 1, because 2e to the minus x times 1 would get us back to here. And so now what we have is very simply the derivative, but factored. Why is that important? Because we're going to set it equal to 0. And e is easy. Remember that, because e to the anything cannot equal 0. So it's not going to factor into your critical numbers. In fact, it's always going to be positive. E to the anything will be positive, which is great news. So all I set equal to 0 is minus x plus 1 equal to 0. That's going to be x equal to 1. We subtract 1 and divide by negative 1, or just add x to both sides. So x equals 1 is a critical number. So let's take a number line. We've got all real numbers being represented here. There's no restrictions on x or e to the minus x. Your only critical number is 1. So let's do a test value into this. Let's pick negative 52,000. Okay. Minus 52,000 is positive. Plus 1, still positive. Times a positive is positive. So what that means is f, right, prime is positive. So the slopes on f are positive. So we're increasing on that interval. And then to the right of 1, 82 billion. Negative 82 billion for x plus 1 is negative, times a positive number is still negative. So that means we're decreasing on f. If we go from increasing to decreasing, or f prime's positive to negative, we've got a relative maximum. Nice. So a relative max. Now it says find all the local extrema. So it doesn't say to justify it here, but if you were asked to do that in the A, B, or BC exam, you would say since f prime changes from positive to negative at x equals 1, there is a relative maximum there. That's a perfect justification, if I do say so myself. Okay, on to this next little part here. Well, we've got a relative maximum, so I'm going to write that out. Relative maximum, or local maximum, at, and that would be at the point 1 comma. Remember, you've got to plug in 1 into the original function. We want to know the y value. That's going to be 2 times 1 is 2, e to the minus 2. So 2e to the minus 2. Some teachers will have you write that as 1 comma 2 over e squared. That's it. That's your relative max. Now, we're going to find points of inflection, so we need the second derivative. Okay, to find the second derivative, one thing that I would advise is either use this form or this form, doesn't matter. But if you're going to use this top form, let's clean it up a little bit. Just a little bit. Okay, so that's our first derivative. Let me kind of segue this off here. Not segue it off, but cut it off. And let's go find the second derivative. All right, so f double prime of x, going after the point of inflection. Well, 2x e to the minus x, if you notice, is the original function. We have the derivative right here, right? So you could do the derivative again, or just notice that its derivative is right there. So that would be 2x, and don't forget we had a negative there. Ooh. We had a negative sign there. Don't forget that we had that negative 1 out in front of all of that. That was important, right? That factored out to be that minus x. So that negative means we're going to have the opposite of whatever this derivative is. So what that means is we've got this derivative, right, came from the derivative of that positive part. So now I'm going to have the opposite of all of that. So I've got the opposite of negative 1 is positive 1. So we're going to get 2x e to the minus x, and this will be minus 2e to the minus x. Again, I've got the opposite of the original function, so I'll have the opposite of this derivative. Not bad. Okay, now the derivative of this is going to be plus 2e to the stuff d stuff. Not so bad. So now all I've got left to do is, again, factor out that greatest common factor. So I've got a 2e to the minus x in everything. So I take that out, 2e to the minus x, and that leaves me with x here, minus 2, and then 2e to the minus x factored out, and a minus 1. Ah, not so bad. So I've got 2e to the minus x times x minus 3. We set that equal to 0, and we'll get that x minus 3 is equal to 0, so x is equal to 3. So that's a possible point of inflection. Let's check it out. Okay, well, this is the second derivative, and the possible point of inflection is at 3. We're going to check out what's going on f. So let's test some values. I'll pick 0. That's a nice number. If I plug 0 into this, I get a negative number in here. This right here is always positive, so negative and a positive multiplied is a negative. So I go concave down, and then I'll plug in like 82. Minus 3 is positive, times a positive number is positive. And so now we're concave up. So what that all adds up to be is that we change concavity from down to up at 3. So therefore, we've got a point of inflection at x equal to 3. So that'd be the point 3 comma, and we plug 3 into the original function. That'd be 2 times 3 is 6, e to the negative 3. And so that ends up being 6 over e cubed. That's all this problem wrote. It's a good one. A little confusing, I think, right here with what I did with using the old derivative, but I just want to point out again, all I did was take the derivative that we got from the first function and say, well, we want the opposite of that derivative. So I just took opposite signs. Just make it for less work. All right, y'all. I'll see you in the next video in the exercises. Peace.